In section 14.1, we are looking at double integrals over rectangular regions. So let's get started here by recalling that in R2, we approximate the area under a curve y equals f of x over some closed interval a to b, such that f of x is greater than or equal to 0 and continuous over this interval by taking the sum of n rectangles. So let's quickly review this process. So if we divide our closed interval a to b into n subregions, we can then approximate the area under this curve using the area of the kth subregion. So we know that the area of this region will be approximately equal to the sum from k equals 1 to n of f of x sub k multiplied by delta x sub k. And this is where your f of x sub k represents the height. And let's give ourselves a little more room here. So we know that f of x sub k is the height of that kth subregion. And delta x sub k is the width of our kth subregion here. So this gives us an approximate for the area by taking the sum of the area of each rectangle. So then we make this process more accurate using Riemann's limiting process. So we want to recall that as the number of rectangles increases, or as n approaches infinity, the width of each subinterval approaches 0. So we can find our exact area here by taking the limit as delta approaches 0. Right, that partition P, the magnitude, the length of that partition is approaching 0, of the sum from k is 1 to n of f of x sub k times delta x sub k. And so as we apply Riemann's limiting process, we are left with the definite integral here from a to b of f of x dx. And our definite integral gives us the area under the curve over that closed interval from a to b. And what's great is a similar process holds true for the volume of a solid in 3 dimensions. So let's go ahead and explore that. So again, a 3-dimensional solid bounded by a surface z equals f of xy and some region r in the plane, so in 2 dimensions, is approximated by taking the sum of n boxes. So let's go ahead and look at the volume of the solids in 3 dimensions. So to get us started, we let z equals f of xy be some non-negative function, and we're going to let r in R2 be a region in the plane. So this is our rectangular region. And we define r here as the set of all points, x, y, such that x is greater than or equal to a, less than or equal to b, and y is greater than or equal to c, less than or equal to d, where a, b, c, and d are all scalars or constants. So making a love note here to ourselves, just like we saw in 2 dimensions, by dividing this region, R in R2, into n rectangular subregions, we can approximate the volume of the solid using our kth subregion. So we can say here that the volume, and we should give ourselves a little bit more room, the volume can be approximated by the sum from k is 1 to n of f of x sub k, y sub k, multiplied by delta a sub k. So we can actually further expand this and rewrite this as the sum from k is 1 to n, again of f of x sub k, y sub k, and this delta a sub k here is the area of that rectangular region. So we can rewrite this as delta x sub k times delta y sub k, right, the area of that rectangle. So this is where, again, just as we saw in the previous case, f represents the height of that kth subregion, and here are delta a sub k, which is delta x sub k, delta y sub k, Or we could even write this as delta y sub k, delta x sub k. It doesn't matter. This is the area, or your length times your width. So we know that length times width times height gives us the volume. And again, this isn't sufficient, right? We want the exact volume. We don't want an approximate volume. So to find that exact volume, we apply Riemann's limiting process. So again, we keep in mind that as n approaches infinity, the area of our subregion approaches 0. So the exact volume here, we can say is equal to the limit as delta approaches 0 of the sum from k is 1 to n of our height, that f of x sub k, y sub k, multiplied by the change in the area of that kth subregion. And this produces a double integral. We have our double integral over that rectangular region R of our multivariable function f of xy, and our differential here is dA. And we should be mindful that there's two representations for dA. So again, R is that rectangular region xy. We can even write this as the closed interval AB multiplied by the closed interval CD. That is our rectangular region of integration. And then our differential here, dA, is equal to the change in the x values times the change in the y values, which is also equal to the change in the y values by the change in the x values. So which order of integration you decide to use is up to you in most cases. However, as we'll see, some cases are substantially easier to use one order than the other. And in a few cases, we can only use one order. So let's now explore these cases and explore our formal definition of the iterated integral.